Hi everybody and welcome to another science video. Today we are going to take a look at Universe Sandbox, and we start especially with this particular video. You see the solar system from the top view, and we see a perpendicular view to the sun and also the other objects of the solar system. And if you take a look at the movement of the orbits, then you will see that every object is moving in something called a prograde orbit, because they are revolving around it in a, let's say, common direction, namely anti-clockwise. But the question is retrograde orbits, so orbits that revolve in the other direction, impossible, or are they possible? Well, there are of course other solar systems as well, and there's no, like, I would say, a particular rule, but the point is that over a long time, objects tend to move into one particular direction. This is also due to the momentum that is like residue of the last star, the last cloud that was forming and also rotating in a particular direction, so it was preserving momentum. However, sometimes object may go into a prograde orbit, for example, due to heavy gravitational perturbations, maybe due to collisions or something like that. And of course there are retrograde orbits or particles or objects in the solar system, but mostly are prograde. And the question is, what happens with a retrograde orbit in the long time? And for this we are going to use Universe Sandbox with a very simple animation to show you what is going on. Let's go. Well, we just jumped into Universe Sandbox, and I would say that we are, well, I just paused it. We are going here to the menu, then we go back to the new simulation. It's basically empty, and let's see how we can create our own small solar system with retrograde and prograde orbits. First of all, I would suggest that we click here on the plus sign and then take sun as a center point, like for example our sun, and then we are going to take heavy planets to play around, because, well, then the gravitational perturbations in effect are more apparent than from smaller objects. So let's pause it first here, and let's move one Jupiter. So we take several Jupiters. Let's say we take one at, let's say, 1 AU. We take another one at, I would suggest, something like 2 AU, and then maybe a third one at 3 AU. There we are. And now we take the Earth, for example, as a smaller object with less gravitational mass, put it to 1.5 AU roundabout. We close this window here, we click on the Earth, and we need to check to make the orbit move into the other direction, because if we play it now and pace it up a little bit, you will see that all objects are revolving in the same direction. But we want to prevent that, and for this we are going to motion, then we go to the inclination part and increase it to 180 degrees, and that way it will remove clockwise. Very well, we can now, for example, take a look at the eccentricity and then plot the graph to see how the changes are happening, because the thing is that just before we start, just centering the sun, the thing is, before we start, you have to know that that it doesn't mean that the planet will be kicked out or immediately fly into the sun or something like that. This takes a lot of time, probably millions of years. We can just take a look at the small effects that are happening in the short time. So I would suggest let's start the play button and see the effects of the eccentricity part. So we are increasing now the time a little bit more, and you see here on the left hand side the eccentricity, how it already starts to change because of the different gravitational perturbations of the different planets here, and it changes and swings by between different values. Now we increase the time a little bit more, becomes a little bit hypnotic, but the thing is, when we increase the things to years, for example, and maybe I should also redo it a little bit with a better resolution, then we can take a look here at eccentricity, go to the graph again, pace up things, and then let's go. So yeah, now it's gathering a little bit the data, and we increase it even more for more years. You see that we have the variations. Now you can say, well, could life exist on this planet? Well, at 1.5 AU apparently not. But the thing is, with the different eccentricities, also the temperatures change all the time. And now we increase the things a little bit more to 100 years per second. And then we will see that at some point the solution is not very stable. And we already see now 0.1 as an eccentricity. We see it's already very, very elongated in a way. Let's reduce the pace a little bit. And oh, and there we see we had a moment where the Earth was kicked out. So the eccentricity was before at 0.1. And then out of bad luck, it really got kicked out of the solar system after around, well, even 1,000 years in our case. But well, to be frank, this is of course in a very extreme case with a lot of Jupiters in a solar system. Now in our solar system, we don't have 3 Jupiters, right? And also the distances are larger, but asteroids that are revolving at certain areas, they do not have a long surviving time. Either they're becoming so eccentric that they crash into another object, or they are ejected. So if we continue playing, then we see planet Earth is leaving us behind, and leaving behind a solar system that is exclusively prograde.